Welcome back to Computer Lessons.
For the last few videos, we have been talking about electricity moving through copper wires and radio waves moving through the air. But electricity has a problem. It encounters resistance, generates heat, and degrades over long distances. To build a truly global internet that connects continents, we needed something faster, lighter, and immune to interference. We needed to harness the fastest thing in the known universe: light itself. This is the world of fiber optics, the hidden nervous system of our planet. While you might connect to the internet via Wi-Fi, that wireless signal only travels a few meters to your router. From that point on, your data is converted into pulses of light and shot through hair-thin strands of pure glass. These strands carry 99% of all international data traffic. The physics behind this technology relies on a principle called total internal reflection. Imagine shining a flashlight down a long, mirrored hallway. The beam bounces off the walls and travels forward. Fiber optic cables function similarly but use glass instead of mirrors. The core of the cable is made of ultra-pure glass, surrounded by a layer called cladding. The cladding has a different refractive index than the core, acting like a mirror that traps the light inside. When a photon tries to escape, it hits the boundary between the core and the cladding and is reflected back inward. This allows light to travel for practically infinite distances, bouncing billions of times without escaping the cable. There are two main types of fiber optic cables used today: single-mode and multi-mode. Multi-mode fiber has a wider core, allowing multiple beams of light to travel simultaneously at different angles. It is cheaper and uses LED light sources, making it perfect for short distances, like connecting servers within a single data center building. However, over long distances, the light beams in multi-mode fiber start to blur together, causing data corruption. This is where single-mode fiber becomes essential. It has a core so microscopically thin, about 9 microns, that only a single ray of light can travel through it directly down the center. Because the light travels in a straight line without bouncing, there is almost no signal degradation. Single-mode fiber uses high-powered lasers instead of LEDs and can carry data for dozens of kilometers before needing amplification. This is the technology used to connect cities, countries, and continents. The most impressive feat of fiber engineering lies at the bottom of our oceans: submarine cables. Contrary to popular belief, satellites carry less than 1% of internet traffic because they are too slow and expensive. The real internet is a physical web of cables, some as thick as a garden hose, resting on the seabed. Laying these cables is a monumental task requiring specialized ships that carry thousands of kilometers of cable on massive spools. The ship slowly traverses the ocean, unspooling the cable and burying it in the sand near the shore to protect it from anchors and fishing nets. In the deep ocean, the cables simply rest on the floor. These cables are not just glass, they are armored beasts. The fragile glass core is protected by layers of petroleum jelly, copper tubing, polycarbonate insulation, aluminum shields, stranded steel wires, and polyethylene. This armor protects the data from high pressure, saltwater corrosion, and even shark bites. Yes, in the 1980s, sharks were attracted to the electromagnetic fields emitted by early undersea cables and would bite them. Modern cables have shielding to prevent this, but the biggest threat today comes from human activity. Fishing trawlers dragging nets across the ocean floor accidentally sever cables every year, causing internet blackouts for entire nations. Even with perfect glass, light eventually fades as it travels through thousands of kilometers of water. To solve this, engineers install devices called repeaters or amplifiers every 50 to 100 kilometers along the cable. These are powered by high-voltage electricity sent through the copper layer of the cable from the shore stations. The most common amplifier is the erbium-doped fiber amplifier, or EDFA. It uses a fascinating quantum trick. It dopes a section of fiber with the element erbium. When a weak signal hits the excited erbium atoms, They release their energy as more light, instantly brightening the signal without converting it to electricity. But one color of light is not enough to satisfy the world's hunger for data. Engineers developed a technology called WDM, or Wavelength Division Multiplexing. Instead of sending just one red laser, they send a rainbow. They transmit dozens of different colors simultaneously down the same strand of glass. Red light carries one stream of data, blue light carries another, and green light carries a third. At the receiving end, a prism separates the rainbow back into individual colors. This allows a single cable to carry hundreds of terabits per second, enough to stream millions of 4K movies at once. Once the cable reaches land, it connects to a landing station, and from there, the backbone network distributes it to cities. But getting that speed to your specific house is the final challenge, known as the last mile problem. For decades, we relied on old copper phone lines using DSL technology. Today, we are replacing copper with FTTH, or fiber to the home. This brings the glass strand directly into your living room. The device on your wall, often called a modem, is technically an ONT, or optical network terminal. It converts the incoming pulses of laser light back into the electrical signals your router understands. Working with fiber requires extreme precision. You cannot just twist two glass wires together like copper. The light would leak out. Technicians use a machine called a fusion splicer. This robot aligns the two glass strands with microscopic accuracy and melts them together with an electric arc. The result is a seamless piece of glass where the joint is invisible to the naked eye. However, fiber has one major weakness: it is fragile. If you bend a fiber cable too sharply, the light can no longer reflect internally, causing signal loss. If you bend it further, the glass shatters. This fragility is why fiber cables are heavily jacketed in Kevlar, the same material used in bulletproof vests. Despite the physical challenges, fiber optics are superior in every measurable way. They are immune to electromagnetic interference, meaning a lightning strike or a power line won't corrupt your data. They are also more secure. Tapping a copper wire to listen in is relatively easy. Tapping a fiber cable requires physically breaking the glass, which immediately cuts the connection and alerts the provider. It is the gold standard of modern communication infrastructure. But fiber only connects fixed locations. What happens when you leave your house? You disconnect from the glass and reconnect to the air. However, unlike Wi-Fi, which covers a room, this next technology covers the planet. In the next video, we will explore the history of cellular networks. We will trace the evolution from the analog bricks of 1G to the digital revolution of GSM, and finally, the high-speed world of 5G.
Tell me in the comments, is your home internet connection pure fiber, FTTH, or are you still relying on older copper technology like VDSL or cable? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.